Okay, so let's continue. So today, so actually, this is the somehow the complement of the last talk. So that's the one conjecture I would like to share with you, the so-called singular pre-silting conjecture. So just to recall briefly that if T is any triangulated category, then so for object in T is called the pre-silting if the homes. So just for simplicity, so the shift homes are zero for n positive. So this T means home T. So it's called silting if it is pre-silting. Sorry. It's pre-silting plus the sixth subcategory generated by M. It's the whole T. So the so-called the category I would like to share with you, the so-called the singular pre-silting conjecture. So let's just write SPC. So this is proposed by Chen and Hu and Qin and Wang. Actually, also somehow implicitly in Yang's paper. Anyway, so the conjecture states that if any lambda is an Artin algebra or finite dimensional algebra, say there's no non-zero pre-silting objects in the singularity category of lambda. So this is the statement of this conjecture. So why this conjecture is of interest? So the thing that just a very well known conjecture by Auslander-Renton conjecture. So this is very old. I suppose goes back to 1975. So it says that again, this lambda is an Artin algebra. M is any module with such that the extensions of M the sum of lambda is zero for any bigger than zero. This implies that this module M is projective. So it's well known that this Auslander-Renton conjecture is when lambda is self-injective, it's also called Takikawa conjecture. So why this the singular or pre-silting conjecture is of interest? I think this is the following observation. Actually, rather easy observation. So this singular pre-silting conjecture implies the Auslander-Renton conjecture. So this is Auslander-Renton conjecture. And if lambda is Gorstein, then these two conjectures are the same. Yes, that's so this proposition should justify the so-called singular pre-silting conjecture. I mean, just for the proof, I just briefly say recall that we this category. So this is by definition the module M, which is orthogonal to lambda. And we know that this category, the stable category of this category is fully faithful, like embedded in the category of singularity. Then yeah, then if so if this holds, no, sorry. If this holds, then this implies that M in the singularity category is pre-certain. Okay, then basically you can conclude the proof. And if lambda is greater than the singularity category is the same as this orthogonal, then this are equivalent. So yes. For this singular pre-certain conjecture is somehow is new. That just mentions one or two results. One is that I mean, so the conjecture says there's no non-zero pre-certain objects in this singularity category. Actually, we can prove a weaker result. So this weaker result is due to, in the self-injective case, it's due to Hayara, Homa, Miyamoto, and Wang. And later we prove this in general. So we prove that the singularity category of lambda has no certain objects. Yeah. So this is not so hard, but I think this observation no non-zero. So this observation, so you see that this is I mean just record this singular pre-certain conjecture. Say there's no pre-certain object, but we only prove the weaker one. So there's no certain objects in the singular category. Yes. So yeah. So second one that this singular pre-certain conjecture holds for some class of algebra. So the so-called ultimately closed algebras. So this includes the syzygy finite algebras. Also, it holds for the so-called singularly minimal algebras. So singularly minimal algebra means the singularity category is minimal. I think this is related to Martin's talk where the triad category is minimal. Simple say. So for say I can say that for very small class of algebras, this conjecture can be verified. But in general, it's widely open. So yeah. So yeah, I just mentioned that this singularity category might be related to the homologic conjecture. So this is somehow the end of the previous talk. So today I will show you another DG enhancement of the singularity category. For this, we have to so first of all, I will talk about the so-called the UNEDA DG category. So for this, we have to assume that lambda is a K algebra. So where K is a field, or we can do it more generally. Say K is a subalgebra or a subring of lambda, where K is semi-simple. But then we can do the quotient space K1. So a typical element is denoted by A overline. And to do the bar resolution, we have to shift. So this S of lambda bar is a shifted module. So means this is so so the typical element here, this is denoted by this. So this guy is concentrated in degree -1. Yes. So this guy is concentrated in degree -1. Yes. So just to recall that it's well known that the bar resolution, actually this is normalized bar resolution. Bar resolution, both B is a complex of bimodules. So the tensors are over K. This tensor algebra of the space, then tensor of. So this becomes a complex of bimodules. And the differentials. So the typical elements identified by this S overline 1n tensor A0 tensor AN. So this is the abbreviation of this element. And A. So this is a typical element in B of degree -n. And then the differential, yes, so the differential of this element. So this as euro. So how to say? So this A1 A0 times. So the tensors are getting shorter. And there's a summation -1. So A0 times A1 comma I -1 times as AI. So this is the multiplication. Yes. Tensors I2 and A. And the last term is minus n A0 times SA1 and -1 times AN. And that's when n is 0, say this term goes to 0. So that's some well-known facts about this bar resolution. So first of all, this bar resolution is quasi-isomorphic. So there's a quasi-isomorphism. So this is a quasi-isomorphism to lambda as a bimodule. Yeah. So so this is a projection resolution. Secondly, there's a co-product of lambda of B. Here, this tensor is over lambda, and the co-multiplication is explicit, so that's right. It's AN. So this is just given by split up. Or take sum of all possible split. S1 I times 1. And then the tensor, here the tensor is over lambda. 1 tensor S I plus 1 n times A n plus 1. Okay. Moreover, this delta is co-associative. So in other words, this B together with the co-multiplication and epsilon is a co-algebra. It's a co-algebra in some certain category. In some category. So actually, this co-algebra is quite important. Having this co-algebra Then, so this construction is taken from Keller's 1904 paper. So one can define the so-called the bar-digit category. So we are denoted by B. So the objects, so that's objects same as so we just when we only consider this the bounded complex with of finite generated projective modules. So the interesting thing is the morphism. The morphism in this category, when there's two objects P and Q in this category, then the morphism here is given by the home morphism from the B tensor P. So this is B tensor P is also a projective resolution of P. So actually, in this case, it's quite isomorphic to P, but it's much bigger. So this is the home complex in the DG category B, and the composition is given by delta. So F is from B, so 4, and G is from say Q to another complex S. Say. Then the so-called convolution, some kind of convolution, T star F. So it's given by this. So it's coming from P to S. So first of all, we do the delta on B. So B split up. Yeah. Then we can use F. So I mean, this applies F, then this go to Q dot, and then use G to S. So compose this. So this is the convolution. So this convolution is the composition in this category. Yeah. So this is so-called bar-digit category. And then I mean yeah. Some facts about this category. So actually, this category we want to somehow to unpack the definition a little bit. So we write out everything explicit. So first of all, when we do the tensor of bar resolution with P, so then we cancel something, and then we know that this guy as a abelian group is a big co-product. And these tensors are overfilled. So S lambda, so this small f. So this small f, then tensor n and tensor p. So everything is tensor over field K. And then it has a suitable differential. So I will not write down. So this at a space. So this is a big direct sum. So the home complex of P and Q, then because this guy is a big co-product, so then this is an infinite product, and we take the home. This home over K, so that's we just ignore the K. The home is over K, so this everything is over K. It's over K. This home is also over K. So S lambda of n tensor of P and to n. Yeah. So I mean, this has a suitable differential induced by P and Q. So this complex is we denoted by Y lambda P Q. So this is why it's a big, as I said. So it's a big product. It's where Y N P Q. Yeah. Just a remark. So y0 pq. So with any zero, then this is the Holmes over k p and q. So this is over k, not over lambda. So this is a subspace of y. So we will just delete this down. So the y0, but this is not a subcomplex. That's subcomplex. That's just only a subspace. But here we have a smaller one. So this is smaller. So this is somehow a subcomplex. So you see that the y is much bigger than this home complex. So then by this we together with sorry, this is Zhenfang Wang, we modify this definition. We introduce the so-called the UNEDA DG category y as follows. So the objects are still same. Objects are same. But morphisms are given by the ypq. So we have defined this y. So here, so I like to mention that here the composition is might be of interest. So the composition is, so that's f. Let f be the when nth power of p to q. G is from with mth power to q and s. So actually this f is given by, so is a linear map from here to here. G is from this m's power of s lambda over line to q to s. So the composition we denote by this circle plus dot. So the composition here, sorry. So this is from m plus n tensor over p to s, and on element. Actually, it's very explicit. So it's m times the degree of m, then gx on s of 1m. Yes, right. Fx on s minus 1 minus n times x. So this f, this belongs to q. Then this then gx on yeah, is well defined. So this guy is belonging to the m plus m p to the s. Yeah. So this is the composition in the DG category. So so we just actually rewrite the DG bar DG category. So the bar DG category is isomorphic to the UNIDA DG category as DG categories. So they are really isomorphic. More interesting is that this Y category, this UNIDA category, is isomorphic to the DG category of Chen complex. So and yes, this somehow this is so this Y is a DG enhancement. It's another DG enhancement using bar resolution. So DG enhancement of derived category. So at least the phenomena is left coherent. So the proof is quite easy. Actually for two, for one it's clear. I mean, for two, that we know that this big complex this B complex is the inclusion is a so this is an inclusion is a quasi-isomorphism. Yes. So this is a new somehow a new relatively new DG enhancement of Dirac category. And remember that we are doing quotient on the Dirac category for the singularity category. So here we tend to do a related construction on the unidentity category. So we introduce the so-called the singular unidentity category. Yeah. Yes. So the singular unidentity category is so we have to do some construction on the unidentity category. To how to do that. So to do this, we need the so-called the graded non-commutative differential forms. I mean, this goes back to Kong's equivalent, and it's graded due to Zhengfang Wang. So this is in this case, the graded non-commutative differential is viewed as a DG and the motion factor from Y to Y. So this is the DG and the motion factor. So given a complex object in Y, so this morphism is sent to it's non-commutative differential. So the construction is just very simple, just tensor of this S over lambda over K. I think yes. So this, but remember here you have to be careful. Here the module action. So for any A in lambda, A on this differential form. So the action is is what you expect. So this one. So this is a little bit non-trivial. Yeah, this is the action, and then the differential is clear. So so this is so this is so this is object in Y. Yes. So this is one thing. For the morphism, yeah. So this is a morphism here in Y. Yeah, we want to construct the non-commutative. The differential form should act on the morphism as a differential form P to the differential form to the Q. So actually, when we write everything out, then this turns out this is nothing but the identity on this F lambda, but tensor linearly tensor over K. So this is tensor over K. So this construction is very explicit and everything is trivial. So it turns out this is really a DG and morphism function. Yeah, you have to verify something, but yeah. Yeah, having this DG and morphism function, then we have another one. So we have a natural transformation from the identity function Y to the non-commutative differential form as a DG function. So this is a natural transformation. So for any object P in Y, the theta P is coming from P to omega and P. So this morphism is in the Y1 of P to the omega P. Yeah. So if you recall what it means, that actually this is given, this morphism is really given by identity on the space S lambda P. Yeah. So this you can prove that this theta is a natural transformation. Yeah, actually this is everything we need to define. Yeah. So this is so the so-called the singular Ineda DG category. So this is some. I hope that this is really new. I saw. So this is ideal S Y subnomina. So as before, so objects have no change. So the objects are complex, but the homes, yeah, P and Q. So the homes, this are really given by co-limits of Y, P, so n goes to so here is n. Yes, maybe I write more explicitly. So just Y, P, Q, and Y, P. This is not a differential form. Yeah. So here this should be induced by theta q. Induced by theta. Then we go just repeat. Then we go to infinity. Then take the co-limits. Yeah, then you can define. Yeah, you can define the morphism. I mean the morphism. The composition is defined. Is induced from the original unit activity category. Yes. So yes. So I think the main theorem in this construction is that uh, yeah the construction. So we have this big singular identity category. So actually this is so there's an isomorphism of DG categories of the so this is a singular DG. So this is a DG singular category. So this is what we want. Actually, this is isomorphic to the singular identity category. So yes. So let me mention some ideas of the proof. So I think the main the main idea. I mean, although the proof in our paper is not given like this, but actually the main idea is that here this non-commutative differential form and together with and the theta. So the natural. So remember, we have a natural transformation here. These two things are somehow compatible. Uh, very. I mean, this is not very not very uh, uh, precise. It's compatible with the bar resolution and its truncations. Yeah, somehow on the bar resolution you can do the truncations, but this more or less correspond to the non-commutative differential forms. Yes, so this is what we want to say. To be more precise, so actually the cones. So remember that the theta p is from p to the series, right? The graded no graded non-commutative form. Yeah, this notation also. So yeah, so maybe I say. So this notation also shows that actually these are related to the CDG, to the CDG factor. Yes. So yeah. So that's why we use this omega and C. Yeah. So this morphism is in Y, right? But remember this the this the H0 of Y actually is the derived Yeah, more or less a derived category of this guy, or maybe. So this is you can identify this as lists. Right? So in this category, so this triangle category. So we can talk about the cones of theta p, right? So actually, the key point that the cones. So in the homotopy, the cones are really perfect. The cones belong uh, to this category. So this yes. So actually, yeah. So the cones. So this guy, this is something we want to model out, right? So this is exactly the key point of the proof that why that yes, maybe I might run remark. So 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 we so previously we have isomorphism with the Vogel GG category. Here we have another isomorphism on the singular unity category. Yes. Actually, in some nice case, I think it's possible to relate. Yes. So you can relate directly. Which direction? I think. I hope this direction. So that's some GG function to relate this to different enhancement. Yes. Yes. I think that's possible to do that. Yes. So yes. To summary that we have two uh, yeah, quite different DG enhancement of the DG singularity, but yeah, but actually they are in the homotopy category of DG category they are isomorphic. Yeah. So some applications. So, yeah. So I will not write the detail. So some applications of this singular unity category. So the first one is that so if lambda is say finite dimensional, then we take the same simple modules, which is the lambda modulo the Jefferson radical. So then they use as a objects in the uh, so I mean so actually let's here. So be careful. So actually the construction of the singular unity category. So this P and Q uh, can be relaxed. So P can be any complex actually. Not just not just a complex of projective modules. It can be any complex. So so when we view this lambda as lambda zero as an object in the singular GG category, so then we compute the DG anamorphism algebra in this big category. So I turned out this one you can describe. So this is isomorphic, explicitly isomorphic to the so-called the DG the Levitt algebra of them. Yeah. So this is I will not define this, but in particular, if lambda is given by quiver with admissible relations, then uh, then this uh, then then this then then this category is isomorphic to the DG so-called Levitt path algebra of some other quiver, not just Q. much bigger quiver. Yes. Yeah. So this is yeah, in some situation we can describe the singularity category. Yeah, because this, you remember, this singularity category is just enhancement of singularity category. Yeah, so this is the one thing I is one. So yes, I just mentioned. So yeah, so this implies that, the singularity category of phenomena is isomorphic to the perfect digit category, perfect category, perfect category, derived category, perfect derived category of the left passage, DG left passage. The second application is that if phenomena is left orthogonal ring, uh, we consider this. We first entry is phenomena, but the second entry can be any complex. So actually, they can prove that this is a factor, defines a factor from derived category of big module to the homotopy category of unbounded complex, of acyclic complex of injective modules of lambda. Yeah, so this is a well-defined factor. Is a triangle factor. Moreover, if lambda is Grunstein, this factor is isomorphic to the stabilization factor of Crowder. So what would I mean by stabilizer factor? So actually, Crowder have very explicit, in some sense, explicit recommend for any nozzle ring. So a left-hand side is a cyclic complex of injecting modules. So this guy is included in the whole homotopy category, right? And this guy is a canonical mapped to the derived category of any module. Yes. So it turns out this is a quotient, and then this can be completed into a recommend. Yeah. So. But for the recommend, you have to be careful. So this I is just injective resolution. That means that if any complex take a so-called DG injective resolution of this complex. So this is okay. But this guy, this P, or so I mean this guy is also implicit because this is determined by I. But P bar is mysterious. Yeah, at least for me. So consequently, that A bar is also mysterious. And so the composition is going I, then go to A bar. So this composition is from the derived category to the. So this is the so-called stabilization factor. So this factor, yes, first of all, it's quite it's mysterious because yeah, A bar is not explicit. But it's of I think it's of great interest because this stabilization factor induces equivalence. Yeah. between the singularity category of phenomena with, maybe the identical completion, maybe. With the compact objects is the latter category. Yes. Yeah. So somehow, in other words, that this category, this homotopy category of a cycle complex or injecting modules is a compact completion of the singularity category. Via the stable the stabilization factor. So so here that together with Devon, we prove that at least when lambda is over K, it is over a field K, then the stabilization factor when it's Grunstein case is given by another construction given by the singular identity category. So this S here. Yeah. So this is another application of this above construction. Yeah. So I think I stop here. Yeah. Thank you very much for your attention. Yeah. Yeah. Zhang Yi. Yeah. Yeah. I stop here.
Oh, thank you very much. Professor Yi, are you here? It seems that. Oh, thank you very much, Xiao-Wu.
Yeah, thank you. Thank you very much.
Yes. Are there any questions? I think Professor E is not here. I cannot join. Yeah. Okay, he was the chairman actually. That's why I was waiting for him.
Yes. It's okay. It's okay. Yeah, thank you.
Are there any questions, comments?
Maybe you have a question.
Yes.
Yes. Yeah. Yes.
I think you mentioned that there is a natural transformation from the identity functor to the functor of differential forms, right?
Yes.
Yeah, I'm not confused. I'm a little bit confused with that. Can you show that again?
Yes, sure. Yes, sorry. Yes. So for the differential forms. So here yes. So having given a complex of P, then we define a new complex. So this is just take the tensor over K. Yes. So the tensor over K.
I know this, but I mean the natural transformation. You mean that you mentioned that there is a natural transformation from the identity functor to
yes, theta.
Yes, theta. So
yeah, here, remember that this y1 is by definition the home from K to the S lambda over P to this guy. But at the workspace, they are the same. So these are the same workspace, the same.
Okay. Okay. In this category, the home space is different. Okay.
Yeah, different. It's yes.
Okay.
Yes. Thank you for the question. Actually, I mean the point is that because the homes are very complicated, so that this theta is really a morphism. Otherwise, theta is not a morphism in the GG category. So this makes the GG category interesting. So because this theta, we needed this theta, but now we make the theta a morphism in the GG category. Yeah.
Okay,
this is a key point.
Okay, thank you.
Yeah, thank you.